So let me start by drawing. Today I'm going to talk about how to use this micro-sheaf theory from last time to prove some results in mirror symmetry. And let me start with some kind of pictures which explain the idea. So this is supposed to be. I think I tried to draw this picture last time, but maybe I did it a bit quickly, so I'm going to try again. So this is supposed to be a torus, and I'm going to make some holes in it, and I'll make the holes here. Okay, so this is one hole, and let's make two more. Okay, so now some kind of punctured torus. It's torus with 3 punctures. Okay, so this thing, if you were to glue it together, it would somehow be this kind of. And now, remember we discussed this kind of Liouville geometry, and so I make some kind of Liouville vector field on it. Which points out near the puncture. And if you try and retract, try and give the skeleton of this item, well, it will look like this. Okay. And so you can kind of see that you can just imagine that this is what somehow you can kind of imagine this. And well, let me just draw this again. So it's at least topologically, there's one big circle, and then there's 3 other circles which come off of it. And I'm going to break up this into these. So this let's make some kind of cover of this thing. Okay, so there's some kind of cover of this thing, and so it's 3 of these guys, which I'm just drawing somehow glued together along this kind of inclusion. Okay, and what we learned, what I explained to you last time, is that this kind of micro-sheaves, I'll just write this on this this kind of person. This is coherent sheaves on P1. And what I didn't so precisely explain last time, but maybe I will today, is that so coherent sheaves on P1, it has some maps to, let's say, coherent sheaves on the point at 0 and at infinity, just restriction. And this, I explained last time, there's this functor of taking this kind of micro stalk. That's how I began the talk last time. And there's that kind of like positive and negative micro stalk. I'll somehow discuss this again in a second. And so this is, you know, okay, let's just denote these A and B. Let's call these functors mu A and mu B. And well, the micro stalk was some kind of vector space, complex of vector space. So whatever. Back. And maybe today I will explain that why this is, these are compatible. This isomorphism, you can declare that it respects this structure. And so here, if you imagine I glue something together out of these pieces along this, then that should, in order to get this guy, that should correspond to gluing together these P1s. The fact that the fact, which is kind of advanced, it's an advanced fact in some sense, but it's easy to keep in your head. Coherent sheaves behave well under certain kinds of pushouts, and this micro-sheaves, it behaves well under certain kinds of covers, and these facts together allow you to reduce the statement that coherent sheaves on this guy is the kind of category of this thing into the calculation which I explained last time. So that's the sort of way in which we connect to mirror symmetry. I don't pretend yet to explain to you so much about it, just to illustrate the general structure of the part of the subject I will not discuss today. What I would like to explain more about today, the first thing I would like to explain more about today is the general version of this statement, where P1 is replaced now by arbitrary toric variety. And correspondingly, you will understand, then given the part of the analog of this discussion, will tell you how to prove mirror symmetry whenever the algebraic geometry side is something which is somehow complex, like built out of a bunch of toric varieties glued along their boundaries and so on. This is is similar to the kind of object that that we saw in Philip's talk, except in Philip's talk, the pieces were not toric varieties. Did you have this picture in your talk? I didn't go to it, so
at the end, sorry.
Yeah, okay. At the end of Philip's talk, there was this picture, it was kind of a ball, this ball triangulated, those triangles, they meant something which was not quite P2, but instead some Lewinga item. So I'll explain what to you what to do when all the pieces are somehow toric varieties, and it's an interesting question whether that can be generalized to this kind of setting which Philip was discussing. Okay. So let's begin. So last time we explained that sheaves, I use this kind of notation. This is somehow representations of this kind of quiver. Okay. I think maybe this is explained more in this after school session. And let's think about a similar fact. So I'm going to close up the boundary. Well, then I should identify these two. This should be representations of this kind of quiver. In other words, well, what is this? What does that mean? It means I give a vector space and one endomorphism. And well, that's the same as modules. So since there's a vector space, there's an action of the field. Let's say I work over the field C. And since there's an endomorphism, the endomorphism acts somehow, I put this variable. Okay. So this has another name. It's also called, I'm going to be a bit sloppy about issues of infiniteness and finiteness and so on, and finite generatedness and so on. So I'll write co when maybe I should write q co or id co. Never mind. And the corresponding Fukaya category is you have like a cylinder, and then it has some sort of stop. So this is like the kind of subject which we were discussing last time. But let's, while we're at it, let's just discuss an even easier, simpler instance of this, which is sheaves on S1, whose microsploit is only the zero section. Okay. Well, constant. And well, what does it mean if they should be constant? It has some value here. If you go all the way around, you come back to the same value, but maybe by some, some endomorphism. So this, but to say it differently, in the kind of discussion we're having last time, remember that, last time when I had something like this, or maybe like this, I drew this picture, and the consideration that I allowed microsploit in one direction but not the other, it forced one of these to be an isomorphism and left the other one alone. If I force both to be an isomorphism, and these had better both be an isomorphism, if I then demand these be equal by connecting this up as S1, then I have a point with an isomorph, like two isomorphisms in the same place, but no one promises you these are the same isomorphism. So there's some invertible guy, but not necessarily the identity. Okay, so and that invertible guy, I record its action in this T. This last equality, in case you're confused, this is because this is the ring of functions on C star, and not similarly on. Let's call this. This is just the. This is A1 minus 0. Okay. So good. And now I remind you from last time that so when I had this kind of thing, we began the discussion last time by constructing some functor, which for now I'm going to call it mu at the moment. And this functor, it sends a sheaf to this microstock, this F. I put the thing in the negative part, so let's put minus theta 0. This is the microstock with respect to the function. It's a locally defined function, but that's fine, giving the angle. And okay, so that's some function. And remember, this was some kind of limit of cone, of whatever. And roughly speaking, what it does is it compares the stock here to the stock here. That was the job of this thing. Okay, so we have this this function to vector spaces. And I claim that under this isomorphism, so remember this thing was supposed to be isomorphic to this kind of co-A1. Let's before we go to co-A1, let's look at this kind of mod CT. This mod CT. You can try and calculate what this is. And I claim that this map, in terms of mod CT, it sends a module M, a module M, it sends it to M tensor CT C. Okay, and the map from CT to C is sending T to 0. Yeah, that's what it does. And how do you check such a statement? How do you check such a statement? And the point is, so I just say it kind of roughly. The point is, in terms of this kind of picture which I had made before, T is this map. Okay, and so taking this tensor product, you, of course, cannot now. Unfortunately, I have to say something unpleasant, which is that everything always is derived, and what derived means is that when I say tensor C, you really have to resolve C. Okay, and tensor C really means you tensor with this complex, and that means I take, well, M is a module over CT, so I just take cone of the map from M to it's
one more cone, is that what you're thinking?
What did I?
I mean, could you alternatively replace M like with a resolution by vector bundles and just take the fiber over 0?
Yeah, I could do any of these things. Yeah. So sorry. So this I shouldn't have written M here. I should have written this. I wrote something slightly confusing.
I don't understand why. I think it's okay. M is a
But you just have to understand what M means.
module over CP. That's module over C. It stays M.
Yeah. Okay. It's possible to get confused by this, but it's also possible not to be confused by it. Okay. So, well, if any of that or all of that was confusing, that's okay. I'm going to use it mostly as a black box. Okay, so I was just trying to explain to you how these different structures interact with each other. That's something, it's not fundamentally difficult, but requires certain algebraic manipulation. There's a couple other facts of this kind which I need. And these are a bit more subtle. So here I had this GM in the multiplicative group, and this acts on the affine line. If you don't like these notations, you should just think of this as C stars. And that action, you can ask, so how is it reflected on this side? Or you could ask a more basic question, which is how is the group structure of this guy reflected in this category? Well, you could ask even first the question, how is the group structure reflected in this category? And let me just let me tell you first what's not the answer. What's not the answer, in this category, there's, as for coherent sheaves on anything, there's a tensor product. Okay, but because GM is a commutative group, there's another structure, namely convolution. And convolution is where you have two copies of GM. You take GM times, why is there a convolution? It's because multiplication gives you such a map. And so if I take a sheaf here and a sheaf here, I can pull them both back to the product, I can tensor them and then push forward. Or maybe I can, yeah, and then push forward. And that's the. And so let me just tell you what that corresponds to here. Here, in this locally constant sheaves on the circle, that corresponds just to tensor product of sheaves. This is a fact which is similar to a different fact which you may actually know, namely that when you do the Fourier transform, multiplication goes to something quite strange. Okay, and in some form or another, that's what fact that this is, or some more advanced version of that fact. This is some more advanced version of a Fourier transform, and under this whatever the multiplication structure on this group here, which like moves around all the points and so on, it goes to a structure here which leaves the points of this S1 alone, but multiplies kind of the functions on them. So the statement is that this action gets translated to a tensor product action of the sheaves S1 on sheaves. Okay. Maybe it's worth doing an example. So example. What's an element of? Let's take an element of cos C star. So a sample element of this is the structure sheaf of some point. Let's say x. X is a point in C star. Okay. Now, let's see what happens if I take OX and I convolve with OY. Well, what happens? I get, I'm supposed to go on the product, is a C star times C star. I have the point X, I have the point Y. I tensor this guy with this guy, this kind of delta sheaf with this delta sheaf. Something non-trivial only happens when they meet. And so I get this kind of structure sheaf of this point, O, X, Y. And then I push forward by the multiplication map, which to C star again. And I get O, X times Y. Okay, that's what that convolution is. Well, what happens over here? This map, it sends this point OX to the sheaf, which has somehow stock just the complex numbers, and when you go around, it's the endomorphism multiplication by X. Okay, that's what it sends it to. You can try and do that calculation yourself. I'm going to call that CX. Maybe that conflicts with some notation I had before. Let's call it LX. And if you know about tensor products, then you'll know that LX tensor LY is LXY. So that's some kind of example about why that the convolution goes. I mean, just how this correspondence is working. Should maybe call it an exercise rather than an example. Okay.
You didn't really analyze the action, like you analyze C star acting on C star.
Yeah, I did C star acting on C star. Okay. And then there's one last thing. Yeah, okay. So okay, so we'll use that later, but okay, so but let's think about how to think about co-AN. Well, actually very easy. This is co-A1, you tensor it with itself n times. Seems reasonable, except you have to know what this tensor product means, that I'm not going to tell you. But it should at least be plausible, because after that you could put something here, because after all, this is modules in some sense over k x1 through xn, which is equal to modules over k x1 tensor kxn. And you need to invent the appropriate notion of tensor product that you can take out of the modules. So, well, what about this? So I claim in general that if I have lambda 1 in T star x1, lambda 2 in T star x2, that sheaves lambda 1 x1 tensor sheaves lambda 2 x2. What's always true is this embeds into sheaves lambda 1 times lambda 2 x1 times x2. And this is almost obvious. You take the two sheaves, you tensor them together, you send them here. What is not obvious is whether this is an isomorphism or not. In general, it's probably not. But if lambda 1 and lambda 2 are Lagrangian, this is isomorphism. In particular, from that, I learned that co-AN is isomorphic to sheaves on this thing to the n, S1 to the n. Okay. Well, that's some progress. I want to just show you how to. This kind of drawings probably came up in Ranjan's talk. I want to show you how to draw this lambda 1 to the n. But let's take n equals 2. So I have S1 squared, which is a torus. So let's draw a torus. I have to identify the ends. And how to draw this thing squared. So here it was easier to draw because everything one-dimensional. Now I have to draw a two-dimensional singular locus inside a four-dimensional space. And how to draw it? Well, helpfully, okay, so first I'll draw it and I'll tell you what the drawing means. So this is how you draw it. I guess I'm supposed to do this one. And what does that drawing mean? Well, it means that along this line, or this circle really, I take the negative conormal. And along this circle, I take the negative conormal. And along this point, I take the conormal, which is negative in both directions. Conormal is the part in the cotangent bundle which annihilates the tangent direction to that line. So this one has like a tangent direction here. I can ask which covector annihilates it. Well, it's the one that points this way. Yeah, so that's how it goes. So this is how you can draw this kind of thing. This is a picture of this squared, which lives in G star S1 squared. Then maybe there was some. Did you draw these pictures?
Yeah, I did this for concentrate random.
Okay, so he drew similar pictures. Okay. So what's next? I now want to take so maybe now I should say why I want to do the next thing. You know, like one way to think about P1 is it's C2 minus 0 mod C star. Okay. I have no reason to stop at 1 here. Pn is similarly Cn plus 1 minus 0 mod C star. And most and essentially all toric varieties have this similar form. It's like C something, A minus some locus, maybe not just 0, some Z. And this Z, it's the union of monomial like hyperplanes and so on, like 0 mod some C star to some power. And this C star, it's not a coordinate C star, acts in some diagonal way. Like this C stars act in diagonal. Okay, so this is I'm going to try and eventually understand this guy, and I do it in steps. So far I've understood this part. Now I should understand how to delete something, and then after that I should understand how to take a quotient. And fortunately, the thing which makes this plausible is that in algebraic geometry, we have the two useful facts that coherent sheaves on X minus Y. This is coherent sheaves on X mod coherent sheaves on Y. And take this quotient. In other words, you just set all the coherent sheaves on Y to 0. I should say this is not very useful for writing this down explicitly. And the reason for this is that it's hard to understand how to take Homs in a quotient category. But to prove things, it's useful. Okay, so this is the first useful fact. And then the other useful fact is if I want to take some kind of quotient, some W mod G, G is some group action. Well, there's some sense in which this is true, is the G invariance of this thing. And the sense in which, in order to make that statement true, you have to say the word derived a bunch of times and understand very carefully what invariance means. But I will elide that part of the discussion. You can almost take that as a definition. And how to say, with statements like this, it's the kind of, let me teach you a general lesson about mathematics. Very often in mathematics, you've written down one definition, like coherent sheaves, a quotient, or something. And there's some statement you would like to be true, like this kind of statement. And you discover that for the definition you wrote down, it's false. And then what typically happens in mathematics is for 10, 20 years, people like work very hard to avoid the fact that this statement you wanted to be true was false. They just work around it in various ways, show it's true in various cases, so on. Then 10, 20 years later, someone says, screw it, I'm just going to redefine things so that this was true all And fortunately for us, we're at the point in mathematical history where these statements for the appropriate definitions just true. Okay, so what that means is that if I want to calculate, if I want to prove mirror symmetry for this guy, it's enough to understand, well, first of all, I better understand mirror symmetry for this guy, which I do now. Then I need to understand what happens when I delete someone. And then I need to understand what is somehow mirror to quotienting by someone. And so let me tell you about that. Okay, so I now need to define. So let's keep this here. Let me tell you some general fact. So fact, if I have lambda prime and lambda, both Lagrangian, these lives in some T star X, conic Lagrangian. And if I want to understand sheaves lambda prime X, well, it's always true that this is sheaves lambda X modulo the microstock co-representatives at points, at smooth points in lambda prime lambda minus lambda prime. So there's some words in here I have to tell you what they mean. So microstock, you know, that was this functor that we began life by talking about. It's erased now. But what is this co-representatives? Well, it's a fact that for the appropriate somehow categorical setup. So remember, we had this functor which takes f to f phi p. This is microstock functor. It's a fact in this situation when this phi is, when d phi is a smooth point of your Lagrangian, that in fact this functor can be what's called co-represented. Co-represented. In other words, there exists some object C B P with this property. Okay, it's a true fact. This is a true fact, which is not obvious at all. And the statement is that this guy, I take this category, I take all of these co-representatives, and I just kill them. But why should you think that's plausible? Well, what is this thing? This is, this says the microsupport had better be contained in lambda. And this says the microsupport had actually better be contained inside lambda prime. So the microstocks at points in lambda minus lambda prime should be 0. So here I've just enforced that that's true. Somehow this prescription, reasonable objects, then you have to convince yourself it's correct on Homs. Okay, so this is one true fact. And let me give you an example of this microstock functor. So example. So when I look at this sheaves, this S1, I want to tell you who co-represents this microstock. Okay. Now there's a map from R, actually, whether it's whether it's greater than 0 or strictly greater than 0, I'm going to get wrong here, but there's a map like this, pi, and I can consider the sheaf pi star z, and then up to putting the correct sign here, that's in this category. And by the way, think about what this looks like. It somehow, this map, it winds around somehow forever, not by accident, looking a lot like this kind of wrapped Fukai category object. That's not an accident. And so the stalk of this sheaf here, it has infinite rank everywhere, but somehow like this infinite many copies, it gets shifted by 1 as you go around. And so some exercise for you is that this guy, this is the guy. And so if you want to complete this exercise, if you want to somehow get all the way, like sheaves circle S1 equals sheaves this S1 modulo this person. Okay, that's the kind of thing which I'm saying.
So that's like for points on the problem.
Yeah, on this problem. Okay, so now how much time have I used?
It's like 17 minutes.
Okay. So now I have to tell you, so I told you in principle how to delete. You can read this fact 2 ways. You can read it as telling you, if I want to delete things from the somehow thing controlling my micro support, what should I do? That's one way to read this fact. We want to read this fact the other way, which is if I want to construct an interesting quotient of categories and describe it as someone's micro support, then what should I do? So I'm going to read the fact that way. So so suppose Z is some union of coordinate at subspaces of AN. So for example, it might be just 0, like just the point 0. I'll do the example explicitly in 1 second. Then I define lambda z. This thing, it's going to be, so this is a definition. Lambda z, it's some subset of this thing to the n. And it is the union of conormals to strata which are not corresponding. So this thing, after all, it sits inside S1 to the n at T star. Union of conormals of strata not corresponding to Z. So what do I mean? Z, this S1, it's 0 union. I write S1 like this, and so it's point union this. And so for example, if Z is just 0, then yeah, let's do explicitly an example. Example, if as n equals 2, so in other words, we have that picture. Z is 0 inside C squared, I'm sometimes writing A2 and sometimes C2. Then what? Well, here I have the circle squared, and the relevant strata. The strata, what are they? Here's a stratum. Here's a stratum, and here's a stratum. And what's the corresponding stratification of C squared? It's this thing is a 0 union C star times 0 union 0 times C star union C star times C star. Okay, that's maybe I'll write them in the corresponding colors. So if my Z is just this one, then I should take the conormals to the strata which are not contained in Z. Not as corresponding conormals, not contained in the locus. So okay, the locus corresponding to Z is just 0. Just this is the corresponding one. And so which strata are not contained in there? This guy, and this whole thing. And what are the conormals to that? Well, the conormal to the 0 section, that's already a Lagrangian. So its conormal is just itself. These ones, their conormals are like this and like this. Okay. And you observe, why did I make this definition? Well, I set it up so that this one differs from this one exactly by deleting this piece. So it follows from this fact, that sheaves lambda z, I mean this fact plus that fact about an that we had before, sheaves lambda z S1 to the n is isomorphic to coherent sheaves on an minus z. Because I've deleted exactly the pieces corresponding to the microstocks which somehow match up with Z.
It's a true statement that you delete the point, and if you take this kind of non-compact.
I should. I mean,
Is that?
The precise statement. I think I said that. I think I wrote the precise statement. It's the union of conormals to strata not corresponding here, and the thing which I delete is an open subset of that closed locus. But it's an open subset which basically contains all the smooth points in this conormal. Okay.
Can you say it again? What's the difference between this and that?
In this one, I included this conormal, this piece of the conormal, this point, and this one I did not. That's the only difference.
I mean, is this not the Weinstein manifold for?
Let's just try. Sheaves this equals co A 2 minus 0.
Isn't this the picture where you have a torus and you attach two?
Yes. Well, we haven't attached them yet.
We haven't attached them. Yes, that's it.
Okay. Okay, so now Well, there's one. Well, so that was for deleting something. Now I should tell you about taking quotient. So again, my toric variety T, I unfortunately erased this. It's supposed to be some A, Z mod some group G. And let's write this kind of sequence 1 to G. It sits inside this multiplicative group. This is a different T. This is a compactification of this torus T. And if in this setup, I'm going to want to make the corresponding lattices of characters. So this M is T, GM. Okay, so I have these groups. I make the lattice of characters. No. Always, there's two M's. One of these was, oh no. And this one's supposed to be M. This one's not supposed to be M. Let's just call this, let's just call this what it is. G. So why am I doing this? So let me first, we'll come back to that in a second. But first, I have to explain the basic idea of what's going to happen with this quotient, which is, so, you know, if we want to think about the relationship between sheaves on R and sheaves on S1. So S1, after all, is R mod Z. But what is the relationship between these things? When does a sheaf on R descend to a sheaf on S1? When does a function on R descend to a function on S1? Well, if it's periodic. In other words, if it's invariant under translation. Okay, so you get the idea that there should be something that, okay, there's a translation action on this, you just pull them along with translation. And there should be some notion of taking invariance so that this is true. In other words, if I know the sheaves on R together with the translation action, I can recover the sheaves on S1. But what about going the other direction? So here the situation is a bit delicate, but let's just think about what kind of thing you would like to be true. Okay, so how should you recover the sheaves on R? Well, the kind of thing which you have here, which you don't have there, is you can tensor by that sheaf with some non-trivial, somehow monodromy, the ones we were discussing at the beginning. And going up to R should, and what is that? So there's some action on this thing. There's some action on this thing of this GM. And that action goes by this tensor Lx, which we discussed at the beginning. Okay, and the reason why you have any of these guys in the first place is that this person, it has some fundamental group, and R is the place where that fundamental group is universally trivialized. So that makes at least plausible the following statement. Now, this statement should seem to you a lot crazier than this statement. Okay, and why is that? Well, if you think about like functions on a circle, like periodic functions, how on earth are you going to get all functions from just periodic functions? That's why this statement should seem a little bit crazy to you. Nevertheless, in this world, it's true. And let me statement, which is going to be we're going to use. So the general statement is some form of some kind of Pontryagin duality. So if you go look up the word Pontryagin duality in Wikipedia, you won't find this statement, but you'll find some something one category level down, and you have some kind of just in general, if you have this kind of setup, okay, so in this setup, you're going to have categories acting on by G, and here category means presentable the G category. That's just for the experts. And you're going to have category acted on by L. And if you have, and the statement is that if you have such a category, you can send it to its G invariance. And if you have such a category, you can send it to its L invariance. And first of all, it's a true fact that the G invariants of this category have an L action, and vice versa. And moreover, it's true if you do one, then the other, you're back where you started. Okay? Which is the general case of this example. Now, how do we use this?
Can I just try to understand this example a little bit better? So considering with Lx, it's like it acts on local systems by just multiplying the holonomy, the monodromy, whatever, by that number x.
Yeah, that's right.
So that doesn't have any, like there is no invariant local system. So these are like some complicated.
But if you trivialize the action, if you take homotopy fixed points of the action, you like have to imagine a category on which that acts somehow.
I mean, okay, it's difficult to explain.
Yeah, it's difficult to explain.
Like
an object.
even the top line though, like taking the Z invariance.
Even the top line is not trivial. The bottom line is extremely non-trivial.
Like somehow, are you saying that somehow this Z means that it's like objects equipped with this Z?
Yeah, that's right. Yeah,
Trivial, like a like a linearization of the Z action.
Yeah, that's right. Yeah. I think maybe there is someone where this is maybe trivial. If you take the push forward of the constant sheaf on R, then I think maybe that person, if you do this, it somehow it doesn't know.
It's like some kind of direct sum of everything with x and x squared.
Yeah, this kind of thing. Yeah. Okay. Yeah, by push-pull formula, right? If you have this push forward of Z tensor as Al chi, that's equal to push forward of Z tensor pull back Al chi, which is, and this thing is trivial. As you pull it back to R. Okay, so I want to use this fact and make some kind of conclusion. I want to keep up this picture actually. I I need this still. So okay, so I want to now consider this kind of sequence. So this is just a torus. This is some kind of some kind of cylinder. This is just a Euclidean space. And if I have some element here, I want to take the fiber, which I'm going to call A gamma. It's some kind of torus. I mean, it's basically this torus. And oh, I'm sorry, I have to do that later. First, yeah, but using this same. Okay, we'll deal with that in a second. Using the same business, there's this.
This is a very trivial exact sequence.
Trivial exact sequence. I mean, it's not. I don't know what trivial means. It's not complicated. There's nothing subtle about it. It's a
Rm cross R, torus.
Yeah, you can split it. Yeah. So I want to consider also the related thing, which is this one, Rn mod Zn. This is a cover. This is somehow this is a cover. It's a discrete cover. Yeah, discrete, maybe not discrete. It's some kind of cover corresponding to. Yeah, it's discrete cover. Zn is the fundamental group of this guy. I have some subset of the fundamental group. I take the corresponding cover. That's what this is. And I take the somehow pull back. Here I had this lambda z. Z has nothing to do with these people. I had this lambda z. I take the pullback and define lambda zm. Okay. And now, okay, I'm gonna want this picture in a second, but let's erase everything else here. So the point is that I can study sheaves on this lambda z m of Rn mod m. That's a perfectly good thing to study. Okay, and I can then of this guy I can take the quotient z and mod m. I take these invariants, and because of this this kind of I mean, by the easy part of that discussion, which is now erased, this is the same as sheaves of lambda z zn or Rn mod zn. Okay, I have this thing on the cover. I take invariants. I'm back down to where I started. And this one, remember, this is what we learned, was this is co an mod minus z. That's what we learned so far. Now I take G invariants. G is this G. And taking G invariance is what I had wanted to do here, so that's good. Who knows what it does to this? But what it does to this, according to this Pontryagin duality, is just get rid of this guy. Okay, so that's it. If I let me do this code. But
Yeah,
huh?
I thought you finished there.
Oh, I have to explain one more thing.
Yeah.
Maybe two more.
What is that called? T?
Well, of this toric variety.
Oh, T is the toric, right?
T was this toric variety.
Oh,
Yeah, this one. Okay, but let me in this example explain what is happening. So in this example, this M, I mean, in this example, the sequence here was 1 to C star. There's the diagonal C star to C star squared. I guess quotient also C star 0. And so I have to unwind. When I go up to this M, I have to unwind this kind of diagonal direction. So right now, this thing is a torus, but it ends up being some kind of cube. Right, so I unwind this direction, some kind of like tube. And in this tube, you have this kind of endless pattern. I unwound one direction of the torus.
what is the Q?
Tube. A tube. I unwind this tube and I take this kind of endless thing. And so what I've shown you so far, more or less, okay, there's many somehow details, but what I tried to explain so far is that that this is coherent sheaves on this thing is coherent sheaves on P2 or P1. But that's not what we saw last time. What we saw last time is that if I take a slice here of this tube, so on this slice, you see you have one sort of positive covector and one sort of negative covector. What we saw last time is that on a slice of this tube, you get coherent sheaves on P1. Now, these facts are both true. And in fact, you can deduce the second fact from this first fact once you observe that the geometry in this kind of transverse direction is in a certain appropriate sense locally constant. So that's the most subtle part of the argument, which I don't discuss at all. I can discuss it in the discussion section. And that most subtle part of the argument leads to the somehow, but this is only for the experts, which is that if you've ever seen somehow this kind of mirror symmetry before, you will not have seen this long unbound thing. You'll have seen the slice over this guy. And the slice over this guy, it's exactly this FLTZ prescription. Maybe if you take it through here. And so what you get by the construction I've described is not just the FLTZ prescription, but a whole, I mean, that's at gamma equals 0. You've got a whole family, somehow a whole family of it. And the kind of monodromy of this family is the action, somehow you can identify it with tensor product by line bundles and so on. There's a whole story you can say about it. Okay, so that's what I wanted to say about toric varieties, but I'm probably already way over time. But I'm nevertheless going to take maybe a few more seconds because I promised Umut that I would describe this proof of this Hacking-Keating theorem. And so I'll just say what kind of ingredient. I'm just going to quote for you a different theorem. Because it's a general form of this. It's kind of interesting in the Liu-Ying context. So this is a theorem fairly recent, to Benjamin Gamage and Ian Lee. And what this theorem says is the following. It says that if I have X, a smooth variety, D, this is smooth, D, a divisor in X, divisor, and then H in D. This is again a divisor. Okay, and everyone's smooth. Then the following. So the theorem is that if I study coherent sheaves on the blow up along H of X, and then you from this delete the strict transform of D, is equal to somehow this push out diagram. This is a kind of strange push out diagram because one of these is a push forward map and one of these is a pull back map. But anyway, these guys prove that this is true. Given what we know in algebraic geometry, given what we know in algebraic geometry about how blowups work and the categories of sheaves and so on, it's not a difficult proof. It takes them a page and a half. So they prove this theorem. And what that means is, it's kind of orthogonal to maybe the rest of the talk. But what this means is that when you have the mirror of a toric surface, like this one that I drew, so this is A2 minus is a mirror to A2 minus 0. Okay. And now I draw it in the other way. I draw it as torus, and you somehow you have these conormals, kind of cylinders coming out. Okay. So this is A2 minus 0, and this is conormal circles coming out. And now I choose I choose maybe the divisor inside here. Let's take 1, 1 in here. Okay, I should draw the same. So inside here I have a C star cross 0, disjoint union C star cross 0, this kind of thing. And then I have the 1, 0, disjoint union 0, 1 inside there. And here I consider this this picture. Okay, and what this diagram is saying is it's saying that if you look at co A2 minus 0, that's this guy or this guy, and you consider the this map from this one, which maybe I somehow mentioned in passing but didn't explain in detail. That's the restriction out here. This co of this thing, and then there's like vect plus vect. That's this one. That the blow up of, if you blow up these 2 points and then delete the strict transforms of these divisors, that is the same as attaching these 2 disks. And that's exactly what that theorem says. And so that more or less immediately gives you the proof of this Hacking-Keating theorem. Not in this particular toric surface, but use the appropriate toric surface.
And this missing point 0 should really be missing, or is this there's like They don't write the cluster varieties, but they write cluster varieties up to codimension 2 or something.
I mean, yeah, they're discussing this cluster varieties, but for anyway.
So it's you actually get the cluster variety.
No, I mean, you don't actually get the cluster variety, but for this hacking and Keating business, I mean, you've deleted the boundary divisor, right?
Yes.
So you don't want that point.
Yeah. 0.
Yeah, zero is in the. I mean, that 0 would be if you closed up these guys. Are you deleting the transform of these guys?
I see, but you're deleting 0 kind of before.
It doesn't matter. Yeah, I deleted.
I've just never
Yeah.
seen anything like that goes through this A2 minus the origin. It's the first time that I see it like this one.
Yeah, so it's, yeah, you can you were asking if you can prove it in this way. That's how you prove it.
No, I know you can.
Yeah, it's
Uh-huh.
okay. That's all that I have to say.
Okay, let's thank Vivek for his lecture. Okay, any question in the room? No, I can ask you a question.
Okay.
And how should I see your sheaf category? I'm a little bit confused. I mean, you said something in the beginning, but your sheaf category is the sheaf of unbounded sheaves on skeleton.
Yeah, always unbounded. Yeah,
One part of it, right?
it doesn't matter. I mean, if you really want to write co, you should take compact part. If you, I mean, I said for this lecture, I'm going to ignore all that business. But if you want to do it properly, then I just take always all sheaves, and I otherwise should write into co. Yeah, just complete.
So the properties for co is actually for.
I mean,
It doesn't matter. I don't know the.
I mean, co is the compact part of indico. This is why David Nadler did this thing of taking unbounded and compact part. He somehow he knew that somehow the correct thing to do in the B side is use inco and take compact part, and so he was trying to catch the same behavior.
So if you wanted to understand the mirror statement for a more complicated attachment of curves, then would you go through kind of the local area surface with the nodes of the divisor missing or something?
Yeah, sure. Yeah, you begin with the toric thing. You somehow you keep out those nodes of the divisor because you don't want to include these intersections, right? Because then your handle attachment is has some piece at infinity left even after you attach.
So then you glue these pieces together.
Yeah, you glue those ones in. You invoke this theorem. Actually,
Maybe you also need a gluing here.
the gluing theorem is, I mean, micro-sheaf satisfies gluing theorem.
Yes.
So the point of this theorem is that those guys knew micro-sheaf satisfies gluing theorem, so they knew this had to be true. And so then they just proved it.
I have one question, but I don't know if it makes sense. So there's this square category has this gradient structure, right? So it's actually not unique. So what's happening here when you go? What happens to this structure?
Yeah, that's a bit long story. So you can ask. That's a long story. Let me tell you later. That's a long story.
Okay, maybe let's see other question. You have? What about online questions? Any online questions? I guess not. So let's thank you back again.